In the previous video, I explained the algebraic structures with one binary operation. Those were the semigroup, the monoid, the group, and their commutative versions. In this video, I will discuss algebraic structures with two operations. To make this video self-sufficient, let me provide a quick summary of the key concepts discussed in the previous video. Given a set S, a function with domain, the Cartesian product S cross S, and target set the set S is called a binary operation in S. We say that the binary operation in S is associative if the result of the composition of three elements is the same independently of left to right or right to left computation. We say that the binary operation in S is commutative if the result of the composition of two elements is the same independently of the order of the two elements. We say that the binary operation in S has a neutral element if there is an element, E, for which its composition with any element X, from left or right, is equal to X. If the operation has a neutral element, E, we say that X prime is an inverse element of X, if X prime composed with X, from left or right, is equal to E. A set S endowed with a binary operation is called semigroup if the operation is associative, monoid if the operation is associative and has a neutral element, group if the operation is associative, it has a neutral element, and all elements have inverses. If the operation is also commutative, then we add the adjective abelian or commutative. Hence, the previous list is expanded by the addition of another three structures: abelian semigroup, abelian monoid, abelian group. Now, let a set R be endowed with two operations which we call dot plus and dot times. The notation implies that the dot plus operation will be viewed as additive and the dot times operation as multiplicative. Although it is possible to start with less structure, it turns out that for the most useful structures are endowed with the dot plus operation should be an abelian group. Regarding the second operation, we will require that it is associative. In other words, are endowed with the dot times operation is a semigroup. The entire structure will be interesting if the two operations are not independent. Hence, they should be linked. Obviously, this linking may come in many different forms. Motivated by the standard addition and multiplication, we require that the dot times operation is distributive relative to the dot plus operation. Notice that I have written two distributive identities since the dot times operation is not required to be commutative. The structure we have thus built is known as a ring. If the set R consists of a single element, then this element must be the neutral element, and we call the ring the zero ring. This ring is quite boring. We want to study rings which contain at least two elements. Such rings are called non-zero rings. There is another case of boring rings. Given an abelian group whose neutral element is E, we can always add a second operation such that X dot times Y equals E for all elements X and Y in R. To understand the previous definition, imagine if the multiplication of any two numbers in the set of real numbers was always resulting to zero. Therefore, with the previous definition of dot times, indeed we promote the group to a ring. However, the resulting structure does not provide any benefit, and the ring is known as the trivial ring. Notice that the zero ring is an example of a trivial ring. Since the trivial ring has no real mathematical value, I exclude it from any further consideration. It is important to note that there are some variations in the definition of a ring from book to book. I will not explain all. I will only mention one, which is the most important according to my opinion. Many authors omit the requirement of associativity for the second operation in the definition of a ring. Then, they call the ring associative if the dot times operation is associative. That is, their associative ring is my ring. They also call the ring non-associative if the dot times operation is not associative. According to my definition, their non-associative ring is not a ring. In Lesson 1, I refer to the set of three-dimensional vectors endowed with the operation of vector addition and the cross product of vectors. This is a non-associative ring since the cross product of vectors is not an associative operation. So, in order to be clear, in the following, a ring will always mean associative ring. A ring for which the dot times operation is commutative is called commutative ring. Otherwise, the ring is non-commutative. A ring for which the dot times operation has a neutral element is called a ring with identity. I will indicate the identity element by I. As an example, notice that the set of integers with addition and multiplication is a commutative ring with identity. Perhaps you have never thought about it, but the binomial identity in the set of real numbers, and its generalization to any power, requires only the commutative ring structure to prove it. Let's verify it for the square case. As we do so, pay attention which properties of addition and multiplication are used. Did you notice? We only need the properties of a commutative ring. The unit property was not used, neither the reciprocals. Therefore, the binomial identity is true for any commutative ring. Following the conventions of the standard addition, we can write the dot plus addition of the multiple terms in the right-hand side using the sigma notation. If the ring is a ring with identity, and introduce the zeroth power of an element to be the identity element, we can include the first and last terms into the sigma sum. Notice that I did not define the zeroth power of a neutral element e. We are duplicating the structure of the real numbers in the ring, and therefore all known results will transfer. Now, let's consider the power set of the set S and equip it with the symmetric difference of sets and intersection. In the previous video, I explained that the power set endowed with the symmetric difference is an abelian group. However, the power set endowed with the intersection is an abelian monoid. Therefore, equipping the power set with the two operations establishes a commutative ring with identity. I will demonstrate to you that this ring has some strange properties. Let's indicate the inverse of set X with respect to the symmetric difference by O minus X and call it the opposite of X. It happens to be X, but using the suggested notation is perfectly fine. In this way, anything you know from the addition of numbers duplicates here. For example, XO plus O minus X can be written as XO minus X and equals the empty set. We will call the XO minus X the zero multiple of X. Notice that all even multiples of a set vanish. In addition, any positive power of a set equals the set. Let's look at the binomial identity now. Due to the previous results, it's a trivial equality. But there is more. If the following quadratic equation is given, and its solutions are asked for x, we know that all sets in the power set are solutions. Hence, the equation has more than just two solutions. Similarly, consider the linear equation, which is the equivalent to x times b equals 0 for real numbers. In the real numbers, the latter equation has a unique solution, and this is the 0. However, for the ring under discussion, there are many other solutions besides the empty set. Any non-empty set that has no common elements with B is a solution. Let me state the result with simple words. Non-zero elements can be multiplied to give 0. Motivated by this observation, let's add some definitions. Let R dot plus dot times be a ring whose neutral element relative to the dot plus operation is E. The notation, R asterisk, will indicate the set R without the element E. An element X in R is called a zero divisor if there exists another element B in R asterisk, such that X dot times B equals E. The element X is called a proper zero divisor if it is not equal to E. Notice that the previous definition uses the word zero and not the word neutral. As I explained in my previous video, It is a common abuse of language to use notation and terminology from standard addition and multiplication. I've tried to avoid it, but in this definition, it is not possible since this is the only acceptable term. Recall that the zero ring also borrows its term from standard arithmetic. A commutative ring with identity and no proper zero divisors is called an integral domain. In an integral domain, the quadratic equation x squared equals x has two and only two solutions given by the neutral elements of the two operations. If, in an integral domain, all elements of our asterisk have inverses relative to the multiplicative operation, then the resulting structure is called a field. Obviously, the set of real numbers endowed with addition and multiplication is a field. Sometimes, it is not necessary that the multiplicative operation in the field is commutative. This slightly relaxed structure is known as a division ring. Besides the field of the real numbers, the set of rational numbers endowed with addition and multiplication is a field. However, in addition to these familiar fields, there are many more. We will construct an important series of such fields motivated by our calendar days and clocks. Let's name a clock by the letter Z, borrowed from the set of integers, with an index equal to the number of hours of the clock. Mathematically, the clock is identified by a set which contains as many distinct elements as the number of hours of the clock. Most often, the elements are chosen to be the first natural numbers starting at 0 or 1. When we talk about time and days in everyday life, we add and multiply hours and days. However, it is well known by our experience that the operations of multiplication and addition in the clocks are not identical to the standard operations of addition and multiplication. In the clocks, once we reach the maximum number, we start over at the minimum number. For example, if we have a meeting on day D and say that we will meet in 15 days, there is no day number D plus 15. Instead, the next meeting will be on D plus 1, a day later, unless D equals 7, in which case the meeting will take place on day 1. For this reason, I will indicate the operations by a plus and a dot with the addition of a numerical index to specify which clock I am using. Having presented the idea, I will drop the word clock and I will start referring again to sets. There is no reason to work with multiple sets. We can work generically with a single set having p integers. Also, note that it is a convention if we start counting at 0 or 1 or any other integer. When only a single operation is defined on ZP, the set is selected from 0 to p minus 1 for the addition and from 1 to p for the multiplication. When both operations are defined on ZP, then it's a matter of taste. In some textbooks, you may see the term modular arithmetic to describe the operations of addition and multiplication in ZP, so a clear distinction from standard arithmetic is made. Also, instead of my notation, the standard notation is, and it is read n plus m modulo p and n times m modulo p, respectively. However, I will keep using the plus and dot notation since it is probably more intuitive for those people who encounter the concept for the first time. It is immediate from what has been presented that, in modular arithmetic, we collapse the set of integers to a finite set of numbers. A visual representation is shown in the figure using p equals 7 as an example. The entire line of real numbers is wrapped an infinite number of times around a circle of length 7. The figure shows only 2 of these turns. It is easy to check that ZP endowed with plus p is an abelian group. In my notation, p is the neutral element, exactly as 12 is the neutral element for a standard clock. And given an element n, p minus n is the inverse element. Then, ZP endowed with dot p is an abelian monoid. Finally, dot p is distributive relative to the plus p operation. So, ZP endowed with both operations is a commutative ring with identity. However, in general, it's not an integral domain. It may contain divisors of 0. For example, for Z12, notice that the product of 3 and 4 is the neutral element 12. Therefore, 3 and 4 are proper zero divisors. On the other hand, if p is prime, the equation m dot p m equals p does not have solutions other than 1 and p for n and m. That is, when p is prime, we do have an integral domain. In fact, it is a field. Each element does have an inverse multiplicative element. Identification of the inverse element is not a trivial exercise. It needs some understanding of number theory, so I will omit it. In future videos, I will present modular arithmetic, and the result will emerge quite naturally. At the moment, I will only state the answer using the traditional notation, which is superior in this case. I have now presented algebraic structures with two operations. In a forthcoming video, I will discuss more complicated structures resulting from the linking of two structures. Also, I will post two supporting videos with exquisite applications of fields. One video discussing the doubling of the cube, known as the Delian problem, and one video discussing the game of solitaire. These are just two of the numerous applications of field theory. I hope you liked this presentation. If you did, please subscribe to my channel to help the creation of more videos. Thanks a lot for your support.